Welcome back to another stream. It's been a while, a bit over a week actually, since my last stream. It's just been a lot going on and stuff like that. I mean, yesterday I've been chopping wood for like 5 or 6 hours in the rain, so I'm pretty exhausted at the moment. But I thought I'd stream anyways, even though I'm really exhausted. I feel like I have to stream to keep this project going, or else I will forget everything and have to start from the beginning, and I don't want to restart the whole project again. Or not again, this is the first time doing this, but you get what I mean. And so yeah, it's been about a week, and I don't think I remember pretty much anything about what I wrote last time, which is maybe a positive. This will be a perfect test actually to see how well using AI to learn programming actually works. Because if I don't actually understand anything, then that means that this is totally pointless and I should just go read a textbook or something, or maybe follow a YouTube guide or something to learn Python. But if I actually manage to figure any of this out, then that should mean that I'm doing well, because this is pretty complex, and I mean, I only programmed and streamed for about a week, or should I say like 7 days, and each stream was about 2.5 hours or something like that, 2 hours maybe. So it's not a lot of time, and to have done all this this fast is actually pretty impressive, or at least I think so. But yeah, without further ado, let's get right back into it. So I think the first step is going through each line step by step, and since I'm pretty exhausted, as I already said. Ooh, am I dropping frames? Alright, I think we're back. That was crazy. It was like 10k frames dropped. It was like 5 minutes of outage or something like that. I have no idea why. It came like out of nowhere. I'm not entirely sure where the cutoff will be in the VOD afterwards, because I don't really know exactly. I don't have like a timestamp on exactly when the buffering started compared to where I was in my explanation. But let's just say, let's just continue on and hope for the best. What was the last thing I was talking about? Oh yeah, I was talking about how... No, I was just about to get right into it, I think. So since we did everything here last time, then we might as well just go through it all and try to understand it. And this will serve as a perfect test to see how well I've retained the information from the AI learning. So, okay. To start from the very top, then we have like from future import annotations. And this is mostly for my own convenience, I think. This has nothing to do with the actual running of the program. This is mostly to make sure that the functions that I create and stuff like that don't complain to each other. Like I can reference stuff further down in the program and stuff like that. I can reference stuff further down to the stuff in the beginning and stuff like that to make sure that I don't get errors and stuff like that. And then we have the imports of the modules, and we don't seem to be using sys or iterable for some reason. And then we have the space constant here, which comes this special character that I just copied from here. I don't actually know how to write this character because it's not a underscore. I don't know if you can see that, but the underscore is thicker for one and a bit shorter as well. So I don't really know what this character is even called. It might be a space marker, but who knows. Anyways, then we have the pre-processing segment here. So I should probably go through the exercise goal here again to just to refresh my mind. So exercise 8, build a tiny BPE tokenizer from scratch. What you'll build: a minimal sentence piece style BPE that trains merges from text, encodes text into token IDs, decodes IDs back to text, is reversible for what it sees at train time. Design choices: simple and robust. Work at character level with a special space marker, which is the special space marker here. Each word becomes, and then they have the cafe here, which is the standard text example, argument, input, whatever you call it. BP then merges frequent adjacent symbols into bigger tokens. Work at the character level, so it basically splits everything and then merges the frequent adjacent symbols into bigger tokens. Okay. Pre-processing flags: normalize, NFKC, and lowercase fold, same as your text stat. So this is, we've already done this before. Save a tiny JSON model in quotes. Vocab plus merges plus settings. Greedy encode. Apply merges in the order learned, simple and deterministic. Okay, so then we have the function here called prep text. And we have the parameters text, which is a string, or it doesn't have to be a string, but here we tell it to well, we basically tell ourselves that we expect a string here. Same with do normal or do normalizing, I think, or normalize, which is a boolean. Do lower boolean, and we return a string. And if do norm, then text.unicode.normalize NFKC. So we have the return the normal form from Unicode string unistring. Valid values for form are NFC, NFKC, NFD, and NFKD. So here we're just normalizing the text, and we set the text parameter here to the normalized version of itself. And if do lower, then we do run the case fold here. Return a version of the string suitable for caseless comparisons. So it will simply how do I say this? It will simply lowercase each character that has a lowercase variant and is uppercase at the moment. And then we set the text to that to itself, but in all lowercase. And then we have a backup here, I think, where we set itself to a normalization of itself with the NFC. Even if we don't use NFKC with the do normalize, we still technically normalize. I'm doing air quotes, but you can't see it. And this is for, if I remember correctly, this was for the simple reason of how do I say this? This was simply to prevent any I don't English today. It's been a week since I spoke in English, so my brain is all foggy and stuff. Okay, so this is simply as a backup of sorts. No, not a backup. A what do we call it when you do something as a like an extra measure? Whatever. I think you understand what I'm talking about. Hopefully. This is simply to avoid any minor problems that might crop up otherwise, so yeah. Drinking some coffee to keep my brain stimulated. And then we return text. Let me just grab some more coffee. Okay. And then we have the next function, define words to symbols sequence, text and string, and we want to return a list of lists with string values. Split on any white space, each word becomes a list of symbols prefixed by space. So space always comes first, I suppose. Hi cat, okay, yeah, this is the example here. And we have the sequence variable, which is a list, or here we're just initializing the variable as we're setting it to nothing. So sequence becomes a list of lists of strings. A list of lists. No, a list of... Yeah, a list of lists of strings. Is that how you say it? It sounds wrong somehow, but I think that's how you say it. A list of lists of strings. Anyways, then we loop through each word, I think. Return a list of the substrings in the string. Using sep as a separator string. Or maybe it's splitting all the characters? Return a list of the substring in the string. Substrings. In my mind, that's the words, because each word is a string of characters, and a string is a list of words most often. If it's a text that's readable. And since we have W here, that might be for words. So for word in text split, we loop through each one, and if not W. So if W is empty, is my guess here, then we skip out of the loop and we return the sequence. Otherwise we append, no, that's not the correct. If the W variable is empty, then we do it all again. Like we stop here and then we go again from the beginning. Otherwise we append the space character, which is the constant here, plus the list of the oh no, we append the space character plus a list containing the W, which is the... Okay, so each word is a list in itself then. And we append that list, in a sense. And then we return the sequence. And then we have BPE core pure. So this is after the pre-processing. We have a function called getPairCount. GetPairCount. Sequence parameter, which is a lists of strings, and we want to return a counter of a tuple string. And tuple where is it? Tuple or tuple? I don't remember how you pronounce it. It's probably tuple. Tuple sounds incorrect somehow. Tuple. Built-in immutable sequence. If no argument is given, the constructor returns an empty tuple. If iterable is specified, the tuple is initialized from iterables items. If argument is a tuple, the return value is the same object. If I don't remember incorrectly, then a tuple is simply a constant list. I'm gonna ask. Hey Rufus, what's a tuple in Python?
Absolutely, Angresk. So a tuple in Python is basically an ordered collection of items. Kind of like a list, but with one main difference. It's immutable. That means once you create it, you can't change its elements. It's often used for data that shouldn't be modified.
So you can't like change any of the values at all after it's set.
Exactly, you got it. Once you've created a tuple, it's locked in. You can't reassign any of its elements. If you do need to change something, you'd have to create a new tuple altogether.
Okay. So inside this function here called getPairCount, counts with the variable count is supposed to be a counter of tuples strings. Dictionary subclass for counting hashable items. And we set it to counter function, or the counter class, I should say. Or maybe not. This is a bit confusing, I'm not gonna lie. And then we loop through the sequence, through every sequence in sequences. And then we loop through each string in that sequence. And we do something interesting. Yeah, I'm going to need some more information on this right here. It's a bit too much to understand. This is kind of confusing. Break it down for me. Okay, let's unpack this line by line with a tiny example. What the input looks like. Sequences is a list of token sequences. It's a list of token sequences. One per word, where each word is split into symbols and prefixed with the visible space marker. Example text, cafe cats. After pre-processing plus splitting, then the sequences here with a list of lists looks like this then. That makes sense, I think. Yeah, it makes sense. And then line by line signature, list string, list of sequences. Each sequence is a string, is a list of string symbols. Returns counter, tuple string, a multiset dictionary like that maps a pair of symbols A, B to how many times it occurs. Maps a pair of symbols to how many times it occurs. Okay. Initialize the counter. So set it to I mean, we set it to a counter, but I'm a bit confused about why we have this here. I'm just going to like pretend we don't have this here in the middle and move on. Think default int missing key starts at 0. Here we even have the the mapping and stuff like that. Outer loop over sequences. For sequence in sequences. Handle each word symbol list. Yes, makes sense. Inner loop over adjacent positions. Range len sequence -1 walks indices 0 to length len sequence -2, so sequence I plus 1 is always valid. Okay. Sequence I and sequence I plus 1 is a adjacent pair. Increment that pair's count. And then we return the all paired frequencies. I think I'm starting to get it, but it's still a bit fuzzy. Step through on the example for cafe we record. I don't know why it says Arduino here, but anyways, so this becomes a pair, and this a pair, and this a pair, and this a pair. And the same like that, okay. I mean, that much makes sense. And then we count them as well. This is exactly what PP needs to decide which pair to merge next. The most frequent one. Y tuples Y counter. Pair like CA needs to be a hashable key. Tuple works great. I don't know what a hashable key even means, but that might come up later. Counter is a convenient dictionary of counts, which helps helpers like dot most common. Edge cases: if a sequence has fewer than 2 symbols, it contributes no pairs. How many words are less than 2 symbols though? I mean, like the word I only has 1 symbol. Is that why we use the space marker perhaps? To make sure like a 1-letter word like I actually becomes 2 symbols in this case. The space marker is just another pair, keeping it less model learn start of word merges like _c, which is useful. Same logic, a bit more Pythonic. in zip. This seems more complex and simpler at the same time. I'm just going to stick with the original version. But it is interesting to see how you can like simplify it like this. But I'm still going to ask about this part here. Why do we set the count variable to a counter tuple string before initializing it as a counter class? It's bugging me that I don't understand this part. I feel like it's important, like a very basic kind of knowledge. I might already have asked about this before, but I've forgotten it, perhaps. I hope that's not the case, but maybe. Maybe. This line is doing two things in one statement. Type annotating the variable count. This is a counter whose keys are tuple, string and string, and whose values are integers, always int for counter. Initializing it as a empty counter. Why bother with the annotation? An empty counter by itself has no key type information. Editors / static checkers, pylens and py treat it as counter any. The annotation tells them exactly what you intend. You get better autocomplete and type checking. For example, this will be flag. Wrong key type, expect tuple. Wrong tuple length. Okay. Downstream types become precise. Collections.counter is generic over the key type. Counter T. The value type is always integer. Okay. The annotation is only for typing. You cannot construct with it. For example, counter tuple string won't work. Hence, we write equals counter and annotate on the left. If you prefer, make it a bit clearer with an alias. I mean, this is probably a lot clearer to me. I'm not going to lie. But I'm not going to do that because that will only muddy the AI and make it more confused. If I do like after edits and stuff like that, so it's better to keep it in the same track as itself to get the most relevant information later down the line. Okay. Anyways, so to summarize, we loop through each of the sequence or the all the sequences in the how should I say it? We loop through each word in we loop through each character in each word inside the text, and then we for each character we basically pair them together with the character that comes after the after itself, and we add a counter to that key, or we add a value to that key to make sure we get an accurate count on how many of that key type there is. In other words, we count the number of identical pairs, and then we return that count as a counter of a counter with the key values of the tuple, string, and string. And then we have the function define merge pair in sequence. Pair. And here we have a tuple of string and string again. And a sequences, which is the list of strings. And we want to return a list of strings. In other words, this sequence, if I'm not entirely mistaken. Here we have merge pair in sequence, okay. So AB equals pair. Okay. So I suppose this means that A becomes this string value and B becomes this string value. It wouldn't make much sense if A and B both become both string values, because it says it's a variable string, and this is obviously a tuple string and string. And then we have a merge string, which is A plus B, token text after merge, concatenate strings. So it's perhaps underscore C or something for the start of the text. And then we have the new sequences. List of lists. Okay, so we just initialize a new sequence or a new sequences list. And then we loop through each sequence in the sequences. We start each loop by setting the variable I to 0 and the variable out to a empty list of strings. And then we loop, or should I say, while I is less than the length of the sequence, as long as I is less than the sequence minus 1, sequence length minus 1, and sequence I, or yeah, iterable or whatever, equals A, and sequence I plus 1 equals B. And then we append the merged. But why do we do this? I mean, we go through the word and check if the pair matches the characters, and if it does match, then we append it to this list of strings. And we increment by 2 since it's a double pair. Or not double pair, but a double character as it's a pair. Otherwise, we append the sequence, or should I say the word character. And since we don't actually append a pair, we only increment by 1. And then we append the list of strings to the new sequence variable. I might understand this, but I'm not entirely sure as well. It's a lot of dense calculations. Here we are. Okay. This is confusing, break it down for me. I'm introducing a lot of noise to this conversation by constantly asking for clarifications, but what else is there to do? I mean, I don't understand it perfectly, so I have no choice but to ask Rufus for clearer instructions, or clearer, not clearer instructions, but clearer explanations. Let's decode that function step by step. Its job: replace every adjacent A-B pair with a single merged token A plus B across all sequences, left to right without overlapping. Inputs shapes. I just don't understand why we're doing this. I mean, there has to be a reason for doing all this, but alright. So input shapes, pair, yeah, 2 symbols, and then we sequence list, many sequences, typical words, each a list of symbols. Yeah, okay. What it returns a new list of sequences where every A-B pair becomes A plus B. A single token string. So is this like a way to switch the sequences from being words to being the pair tokens instead? It might be, if I understand it correctly. Okay, line by line. Unpack the 2 symbols to merge. Okay, yeah. Merge A plus B token and text. Creates the text for the new token. If A equals C and B equals A, then merge equals CA. After merges, tokens can be multi-character strings. That's intended. Multi-character strings. Okay. What's a multi-character string?
So a multi-character string is just a string that contains more than one character. In other words, it's any piece of text that's longer than a single letter. So for example, hello is a multi-character string because it has multiple characters in it.
So that was a lot more self-explanatory than I thought. I thought it was something new. But okay, so it's basically strings with more than one character. Really basic, okay. And then we have the new sequences. We build a fresh list, don't mutate the input. Mutate. I would say don't mutilate the input, but don't mutate works as well, I suppose. For sequence in sequences, process one sequence at a time. Scanning with an index I. Collected transformed tokens into out. And the sequence in question is a word. Well, I should probably not like continue saying it's a word because the text might not even contain words. I mean, it doesn't have to contain words for me to be able to train on it. But when I visualize it in my head, then I see like a text of words, and then I think of each sequence as each individual word. But that might not be accurate always, but I'm gonna continue thinking like that for now, I think. And then we have process one sequence at a time, scanning with an index. I collected transform tokens into out. While if condition at position I, do we see the pair A, B? We need I is less than the length of sequence minus 1, so I plus 1 is in bounds. And sequence I equals A, and sequence I plus 1 equals B. If yes, append the merge token once and skip both original symbols. Yeah, we skip them because we iterate by 2. This is why merges are non-overlapping in a single pass. If no, just copy the current symbol and move on by 1. Store the transformed sequence. After all sequences, return the result. Walk through example. CA merge CA input. So this is the input in this case, which is a list. Or should I say, this is a list of lists, and this is a list of strings. So this is the sequences, and this is a sequence, and this is a Or should I say this is a I when it iterates through each one. So I equals 0, process the first sequence. C underscore and C doesn't match CA. Oh, since it doesn't process the... wait. I'm a bit confused why we wouldn't have like underscore C as a pair. Was that something I missed before? I'm just gonna roll with it and say that we never have the space marker in the pairs for some reason. Okay, so since it doesn't match on I0, we copy the space marker. On I equals 1, CA matches, we append it, and we skip 2 to the third iteration, and F. We copy that since it doesn't match the pair, and same with the fourth iteration. And we stop as it reaches the fifth, and then we set the output to this list instead. And the second sequence similarly becomes like that. And this is then the output, a list of lists of strings. Overlaps yi plus equals 2 matters. Consider sequence AAA and pair AA. I equals 0 matches, append AA, it becomes 2. I equals 2, only one symbol left, copy A, result AAA, non-overlapping. If we had advanced by 1, we'd risk reusing symbols we just merged, which BP does not do in a single pass. Okay, key points and gotchas. Non-overlapping left to right. Each pass replaces all occurrences of that pair once. Tokens are strings after merges. A symbol can be... Tokens are strings after merges. A symbol can be underscore C, CA, CAF, etc. No cross-sequence merges. Can it really be 3 characters? That seems strange somehow, with all this talk about pairs and stuff like that. No cross-sequence merges. Sequences are processed independently. For example, words don't merge across spaces. No vocab updates here. This function just rewrites sequences. The trainer adds the new token text A plus B to the vocab / set outside this function. Complexity linear in total symbols. Each symbol visited once per pass. If you want, we can instrument it to print I the window and out as it walks a short sequence. That's often the quickest way to make it click. That might be the fastest way to make it click, but that will also mean running the program, and I don't feel ready for running it yet. I want to understand it better before I try running it. but I think I understand it in essence. I mean, we supply a pair here, which might be like we have here like CA, or it might be underscore C. This time we in this example here we have CA, and then we just go through all the sequences and we basically optimize the text, or should I say the token data, by converting each character to multi-character tokens. That is my guess, at least. And it makes some sense, I think. Okay, then we have the next really big function. Oh no, it's not that large. Well, it's much larger than the last ones, but it's not gigantic. But it's not the last function either. Train BPE. I'm going to take a short break since my head is feeling all beaten up by all this programming knowledge, to get some more coffee and go to the bathroom. I'll be back in maybe 5 to 10 minutes. Let's say 10 minutes just to be on the safe side. So yeah, I'll be back soon. And I'm back. It's raining like crazy and the wind is literally howling in the rafters. There's been a real stormy weather today. That might be the reason for the previous internet issues in the beginning of the stream. Maybe. Who knows? Anyways, I got my coffee refilled. It's still too hot to drink, but it will probably fuel me through this next part here. So here we have the training function for the BP tokenizer. Bytes per... I've forgotten what the BPE stands for, but I'm fairly sure I asked it somewhere. Okay, I missed it somehow. Oh, here. Byte pair encoding. I'm blind. It's a simple subword tokenization method. Adapted from the 1994 compression trick, where you start with a sequence of symbols, count all adjacent symbol pairs, merge the most frequent pairs into new symbols. Repeat steps 2 and 3 until you hit a target vocab size. Ordinal pairs are frequent. Okay. At encode time, you apply those learned merges in order to split any text into the same subwords. It balances vocabulary size. Small with coverage can represent any word as a few subwords / characters. So rare words don't become unknown or unk. Unk. I have brain rot. Notes that matter for you. Okay. I have practically forgotten this here, so it's actually good to reread this. Why do you need to do this? What's the point? Great questions. Short version, BP, and tokenization in general is how we turn raw text into manageable streams of integers that the model can learn from without exploring memory / compute or running into unknown word failures. Why not use words or characters, short sequences, huge vocabulary, SIP law, millions of rare forms, misspellings, names, massive embedding, softmax, character level, tiny vocabulary, very long sequences, needs long range modeling to learn even simple morphemes, Ingtion Cafe. BP, best of both, open vocabulary, almost no unknowns, compact vocabulary, 30,000 to 50,000, manageable embeddings, shorter sequences, 10 characters, big win for attention, language agnostic, handles names, emojis, code, multilingual text. Intuition. Text has a lot of repeated fragments, underscore the, Ingtion, underscore cafe. BP just merges frequent neighbors, so common fragments become single tokens, rare stuff stays decomposed. This matches data statistics, so the model learns useful subword units without memorizing every full word. Concrete payoffs. Faster plus cheaper training, smaller model footprint, smaller vocab matrix, fewer failures, reversible pre-processing. Okay, trade-offs. Segmentation can look odd. Merges are frozen after training. If you truly need bulletproof coverage, switch to byte level BPE. Okay, next exercise. And okay. So train BPE. And we have parameter string, a parameter vocab size, integer, and do normalize to lower booleans. And we want to return a dictionary. Train BP merges until vocab size is reached or no pairs remain. Returns a model dictionary with vocab list of tokens, merges list of pairs, and meta. Text equals prep text. So we pass it through the prep text function here that does the normalization and the case holding. And then we get a sequences, which is a list of lists of strings. And words to symbol sequences. Split on any white space. Each word becomes a list of symbols prefixed by space. Yes, and here we initialize the sequences. And we split the text and we go through each word and we append it to the sequence with a space beforehand, before returning it. And then initial vocab equals all single symbols used includes space. Vocab equals set string. This is a sim for sequence in sequences for sim in sequence. Okay, I'm gonna need some more information on that one. Explain this. That line is a set comprehension that flattens your sequences and keeps only unique symbols. Set comprehension. I don't think we've even gone through what set is. Like, what is a set? Breakdown. For sequence in sequences, iterate each sequence. Each word is a list of symbols. Yes. And then for sim in sequence, iterate each symbol inside that sequence. Because there's one expression inside the braces, not key value, this creates a set, not a dictionary. But what is a set? sim the expression. Each visited symbol is added to the set. I mean, this has to be a loop of sorts for sequence in sequences, and then this is another loop for sim in sequence. But why do we have a sim here? Or is that like a callback to this one? Or is this a callback to this one? So it's equivalent to vocab set for sequence in sequences, for sim in sequence, vocab.add sim. What you get, vocab is a set string containing every distinct symbol appearing anywhere in your training text. Including the space marker. Sets automatically deduplicate, so if C appears 1000 times, it's still just one entry in vocab. Oh, that makes some sense then. Why here BPE context? This initializes the base vocabulary to all single symbols before you start learning merges. Later, as you merge pairs, you'll add those merged strings to the vocab too. Notes. Empty set is set, not like that. That's an empty dictionary. But since it's not empty, then that means it's a set. That's a bit confusing, but okay. Sets are unordered. If you need a stable order, convert later as you do when building final vocab list. Okay. So we basically add all the characters, or should I say symbols, in the text to the vocabulary. So for some reason, if let's say we don't have this character here in the text anywhere, then that won't make it into the vocabulary list. But if we do have it, then it will. And it doesn't matter how many of those characters we have in the text, it will still only add one to the vocabulary set. Okay, and then we have the merges, which basically just initializes a list of tuples. That's strings, there's two strings. Okay, so then we keep merging the most frequent adjacent pair. Keep merging the most frequent adjacent pairs. So while the length of vocabulary is greater than vocab size, oh yeah, vocab size is a parameter, of course. So while the vocabulary is still greater than the vocabulary size, then pair underscore count, which is a new variable here, I think, yes, equals get pair counts sequences, and this returns all the pairs with their counts. Okay. If not pair counts break. So if pair counts is completely empty for some reason, then we break this loop. Otherwise, we set a new variable, which is a tuple. To pair count or best pair and frequency. To pair counts, but most common. But why do we have a 1 here and a 0? I might need to have the AI help with this. Oh no. Seems I need a lot of hand holding through this programming. Okay. Break this down for me. Can do a exchange of the items here in the meantime. And exchange. And we get another duplicate. Too bad. Okay. Here's that training loop, unpacked line by line and why each piece exists. Okay. What why for each line? While len. So keep learning merges until your vocabulary reaches the target size. This is the main stopping condition, so you don't grow the vocab unbounded. Wait. Oh, okay, that makes much more sense. I did a typo here, so while vocabulary is less than vocab size. Good that I caught that now, and otherwise that would have resulted in some errors probably, or not errors, but some very strange behavior probably that I've had that will require my debugging and stuff like that. It would have probably taken hours, or maybe at least half an hour. So we keep learning merge until your vocabulary reaches the target size. This is the main stopping condition, so you don't grow the vocab unbounded. Pair underscore count equals get pair count sequence. Count every adjacent symbol pair across all sequences words. This tells you which pair is most common right now after previous merges. Okay. Right now. And then we have if not pair counts break, if no sequence has 2+ symbols. For example, no adjacent pairs exists, there is nothing left to merge, and then we stop. So this is just a safety. Or a a safety stop or whatever you call it. And best pair and frequency equals pair so counts at most common. Pick the most frequent adjacent pair. For example, C and A occurring n times using counter.most common 1. Gives you that pair and its count. So that's only a part of the function then. Oh no, it's 1 because we want one result. We don't want a list of like the top 3 or stuff like that. We want only the top result. That's why we use a 1. But I don't understand why we have this tacked on to the end. I mean, this should return a... So it returns a tuple and an integer at the same time. And we set the frequency to the integer and best pair to the tuple. I'll say tuple again, I mean tuple. To the tuple. And then we have, then we check then if the frequency is less than 2. No benefit in merging pairs seen only once. That makes perfect sense. So then we break here. Otherwise we append the best pair to the merges list of tuples. And apply this merge everywhere. So we set the sequence variable to merge pair in sequence, and we pass along the best pair. And the sequence. I think I'm starting to understand how this will all work. Like how the way this will iterate through the text again and again, going through all the symbols and pairing them, and then creating tokens of those pairs before doing it all again from the beginning up to create like bigger tokens. It makes some sense in my mind, but I'm not entirely sure if I'm misunderstanding it or if I'm actually understanding it. But it's very cerebral. I mean, I've never done anything like this before, so just imagining it is kind of straining. I can almost feel my brain like whirring just thinking about this. But if I understand it, then it makes sense. if I don't understand it, then it should also make sense, but I simply don't understand it yet. I don't know. It's hard to explain. But I think I actually get it. Not like what each part of the code does. I still need to go through all of this and like check it through, but like the overall structure of the code makes sense in my mind. Or the process, I should say, maybe. The coffee is definitely helping my brain process all this. I don't normally drink coffee, but in the evening and after a day like this, I need it. My brain needs it. And even with all that, I still won't be able to go through all of this today, I don't think. But at least this function as well. I need to finish this function. That's like the bare minimum, I feel like. Anyways. So where were we? Gives you that pair and its count, the frequency break, heuristic early stop. A pair that appears only once isn't a generally useful subword unit. Merging it would create a very specific token that helps only a single spot. Stopping here focuses the vocabulary on patterns that recur and gives you a clean, compact model. Merges.append best pair. Record the rule in order. Encoding later must replay merges index in this exact sequence to reproduce training behavior. Okay. Sequence equals merge pair in sequence best pair in sequence. Rewrites all sequences by replacing every non-overlapping AB with the single merge token A plus B. This changes the future context. New neighbors appear, so the next get pair counts sees updated statistics. Yes, that makes sense. And then we have the vocab.add. Best pair 0 plus best pair 1. So the A and B in that best pair. We add that to the vocabulary then. Add the newly created token string, for example CA, to the vocabulary so len vocab grows toward vocab size. We don't remove A or B, they may still appear elsewhere. Tiny step through one iteration. So if the sequence is sequences is this, pair counts, tally all the neighbors. Yes, with the yes pair counts here. And we get 2 of the pair counts with a frequency of 2. And then we append them to the merges. But wait, why do we append these to the merges? Is this simply to have a list of the merges? Or does this serve a purpose beyond, like for debugging and stuff like that? I don't see it used anywhere here. It might be used. Oh, so here we have the merges. So it's probably just for the model data of sorts. Like, it probably doesn't impact the performance of the model. It's simply for my own information. It's my guess. Okay, so we add CA then to the vocab. But I mean, underscore C is also, but it's a bit confusing why it says best pair might be. Well, it might be because we have the same number of frequencies, then that's the reason why it just takes one of them. So it's randomizing in that case, just picking one of them. Loop repeats with new pair counts on these updated sequences. And those pairs will be like underscore CA, CAF, and FE, for example, or underscore CA, CA, and T. That would be another pair then. And if cat is something that's written a lot of times in the text, then that might be a new token. Not a new token, but a new vocabulary. Or do you say a new token? Maybe. Does the whole rhythm count, pick best, record, apply, grow vocabulary, and repeat until you hit your vocab target or run out of meaningful pairs. Whichever comes first, I suppose. Okay. Then we have finalize vocabulary as an orderly list, all symbols seen after the last merge pass. Okay, so we're going to order the list basically. Collect from sequences to ensure only reachable symbols are included. Only reachable. I don't really understand what it means by only reachable symbols. Anyway, final vocab list, which is a list of strings, we initialize that, and scene equals an empty set, which is a unordered collection of unique elements. And we loop through the sequence sets, and for each sequence we check each token, and if token is not in scene in this set, then we add the token to the scene set and we append token to the final vocab list. Okay. I'm still not sure what collect from sequence to ensure only reachable symbols are included. I don't know what that means. It might not be really important, but I'm going to check it anyways. Break this down for me. I mean, it makes sense in like the text itself, but there seems to be more to it than I'm realizing. Got it. Here's that block line by line, what it does and why it's written this way. What it's doing in plain terms, we want a final vocabulary list of tokens that actually appear after all merges in a stable order, so token IDs are deterministic. We walk through the final sequences, left to right, and collect each token the first time we see it. Scene prevents duplicates, the list preserves first appearance order. Why not list vocab? Vocab is a set unordered, converting to a list gives an arbitrary order. Token IDs would change across runs. Vocab may also contain tokens that don't appear anymore after merges, they were merged away everywhere. Those are unreachable, we don't want them. So that's the explanation for this here then. I didn't realize that the tokens could like phase themselves out somehow after merges. So we create an empty list, hold tokens in order of first appearance, tracks which tokens we already added, and then we loop through them and only act the first time we encounter a token. We add it to the scene and the list, make it scene, append it to order list, and we have then a p-duplicated ordered list of exactly the tokens that still occur after training. Perfect for turning into IDs. And that's the next here. An example. Bulk them once. See, add, next sequence, already seen, seen, T, add, S, add. Oh, okay. Yeah, that would compress the vocabularies a lot in this instance. Note how single A never appears because it's been merged into CA everywhere, so it's excluded. What about this? Might as well ask it. Took I for I, token in numerates, Final vocab list. Those two lines build the vocab lookups in both directions. What each part means. Final vocab list is your ordered list of tokens, ordered first time each token appeared after training. Enumerate yields index and token. Okay. And what's the... Returns an enumerate object. Took I for I took in a dict comprehension that flips those into a mapping token to ID. Example, final vocab list, stoi. So it maps them to like that. And it to's final vocab list use the list itself for ID token because the list index is the ID. Why do it this way? Deterministic ID. The order of the final vocab list is stable. Same IDs every run. Fast lookups. Encode IDs. Stoi took for took in tokens. Decode texts. JSON ethos I for I in IDs. Compact to save. Store only the list in JSON. On row rebuild stoi with one line. Tokens after merges. IDs. Yes. And decode tokens back. Ethos I for I in IDs. So then we get them back. Okay. And and here we have done the tokens back and replace this character with a space to get a space cafe instead of whatever this Mambo Jumbo is. Comment weeks later, reverse specials prepend boss EOS, then build the story or use enumerate start K if you reserve numeric ranges. Frequency ordering if you prefer most frequent tokens to have lower IDs. Sort for final vocab list by frequency first, then stoi. That's it. Stoi string / token. Ethos IDs token string. Oh, it's even capitalized the S and T and I. But S T O I should be, but it missed the O. But here we have I and T O and S capitalized. I was wondering where it got this stoi and ethos from, but that's done from string / token ID or ethos ID to token / string. Stoi string / token to ID, ethos ID to token / string. Anyways, then we have the model variable, which is a dictionary, and of strings and unknown. So the key meta becomes wait. yeah, the key meta becomes space, and then the character normalize to norm. Okay, so this is the arguments then. And then vocabulary is the IDs to string, IDs to token slash strings. And then the merges is the list of merges in learned order. Will JSONify tuples. And we return the model. Okay. But we don't actually use this anywhere. Well, yeah, it's assigned but never used. That might be one of the 3 problems we have here. Yeah. Whatever. I'm not gonna bother with it. Okay, so we return a dictionary string unknown. What does it say here? It only says a dictionary. Okay. But yeah, that's the training function done, and then we have the apply merges and encode with model, decode with model, and then we have the CLI set up here, which should be... I shouldn't need to use too much brain power to go through all this. Or maybe a bit of brain power on this last segment here. I think I'm going to break it here. I could push through and do these as well, and the last part here as well. But I think it's better if I come back like tomorrow, hopefully, or maybe the day after tomorrow, and then I continue like decoding this arcane script. It will probably make the information that I've learned today set firmer in my mind. Because if I do it all now, then there's a pretty large risk that I'm going to forget a lot of the stuff here to make some room for the later stuff down here. I mean, it's been about 2 hours now, so yeah. I want to start doing a little longer streams than 2 hours, but I'm not really sure how to do that. I probably need to like take more frequent breaks or take some longer breaks. Maybe start a little earlier in the evening and then have like a quarter-hour break or something like that in the middle. It's something I need to think about, but yeah, this is it for today. Thank you so much for watching. Leave a comment and like and subscribe. I would really appreciate it. And yeah, I'll catch you in the next one. Bye.